everybody, welcome back. We're going to do the second day of 3.6, which is basically we're going to be finding all of our complex roots of a polynomial, which is all of our rational roots, which is what we found yesterday, plus anything that's irrational. So we have our real numbers and all of our complex numbers together, which makes up our complex number system, okay? And then we're going to write the equation of a polynomial given its roots also, okay? So first of all, a fundamental theorem of algebra basically says every polynomial that has an n degree greater than 1, so it can't be a constant polynomial, has n roots. So this, whatever the power is, we talked about this yesterday, whatever the power of the polynomial, so this highest power here is a third degree, and this has 3 roots, 1, 2, 3, it has all real solutions. Over here we have some repeated solutions, so we have a 4th degree polynomial, it has 4 roots. We have one root of 1/2, and then we have one that has a multiplicity of 2. So -1 has a multiplicity of 2, so it means it bounces at that -1. And then we have a -3 also. So we still have 4 roots, -3, 2 -1s, and a 1/2. And then for complex solutions, this one has 5 roots up here. So we have one real solution, that's 3, and then we have the other 4 right here. So we have conjugates, positive and -2i, so that's 2 of them, and then positive and -2 square root of 5 over 5. That is 2 of them right there. So a total of 5 roots. 2 imaginary, 2 irrational, and 1 real. Okay, so that's what the fundamental theorem of algebra tells us. You know, we have that many roots. And then we can also tell what kind of roots they're going to be. Okay, so the important notes about this is it's mainly concerned with the solutions of polynomial functions. Okay, the fundamental theorem does not tell us how to find them. We have to actually find them. The fundamental theorem of algebra does not tell us the nature of the roots, okay? Whether they're actually, they tell us what they can be, it doesn't tell us what they actually are. And it just simply states the number of zeros that has to exist. That helps us kind of make sure we find all of our zeros. So here we have this polynomial with a power of 5, that's my highest power of 5. And so how many solutions are possible? Well, we know we have to have a total of 5 zeros, right? And so that's going to be down here. We have to have 5 zeros down here. That means we could possibly have all 5 be real solutions and none of them be irrational, imaginary, okay? We could have 2 of them be imaginary because remember they're conjugates, so they have to come in pairs, right? So they have to come in 2. They can never come in 1 or 3, so they're always going to be even. So if there's 2 imaginary, that means there could be 3 real solutions for a total of 5. Okay, for altogether, complex. So here we could also have 4 imaginary, right? Because one pair is 4. So we have 2 pairs equaling 4, which means we'd have 1 real solution for a total of 5. Okay, so those are our different combinations. So we know that when we solve this, we're going to end up with one of those combinations. Either all 5 are going to be real, 3 real, and one pair of imaginary, 1 real, and 2 pairs of imaginary, and that's it. I can't have 6 imaginary because that would go over what we have, okay? So you might want to pause the video and see if you can figure out what our different combinations of solutions are here, and then come back and see how you do. Okay, so in this case, we have 7 total, right? So we end up with 7 total down here, which means we could have all 7 be real and none of them be imaginary. That would be kind of crazy. The next thing we could do is we could have like 2 be imaginary, which would give us 5 real for a total of 7. We could also have 2 pairs, which would give us 4 imaginary solutions, which would leave us with 3 real solutions for a total of 7 again. The other thing we could do is we could have 6 here, right? 3 pair, which would leave us with 1 real solution for a total of 7. We can't have 8 because that would give us higher than our power, which is 7 here. Okay, so those are all of our combinations of solutions we can have. Okay, so now we're going to actually start finding all of our complex solutions. So we have a power of 3 here. We know that we could either have all 3 of them be real solutions, or we could have 1 real solution and 2 imaginary, right? 1 pair of imaginary. So look in here, I'm going to look and see if I can factor by grouping here, which it does not look like I can because 6 and 23 do not have a common factor. So I'm going to list out all my possible roots. For 6 right here, it's going to be positive -1, positive -2, positive -3, and positive and -6. I'm not going to divide because everything divided by 1 is just going to be that same thing. So that's our possible zeros. Then I'm going to start dividing. Okay, I'm going to divide by 1, 1, 8, negative 23, and 6. Bring 1 down. 1 times 1 is 1. That's a 9. 1 times 9 is 9. That's going to give me what? A negative 14. And then that's not going to be a 0. I can tell that right now. So we're going to do the next one, negative 1, 1, 8, negative 23, and 6. Bring down my 1. That'll give me negative 1 here, 7. Negative 1 times 7 is negative 7. Negative 30, that is not going to be a 0. Boom, boom. Next step will be 2. So I'm going to go 1, 8, negative 23, and 6. Bring down my 1. That's a 2, that's a 10. That's going to be a negative 20, not negative 20. That'll be negative 3, which will give me negative 6, and 0. So we finally found a 0 here. Okay, so that will give me an x minus 2. And we'll have left over, what's that, x squared plus 10x. The writing's not very good. Minus 3, and everything equals 0. So, any factors of negative 3 to add up to 10? There is not. So I can solve this guy using either completing the square, right? Or I can use quadratic formula, right? Quadratic formula probably is the easiest way to go, I imagine. I guess completing the square wouldn't be too bad because 10 is even. So I'm just going to use quadratic formula because, well, it's the easiest thing to do right now over here. So x equals opposite of b plus or minus the square root b squared minus 4 times a times c all over 2a. That's going to give me a negative 10 plus or minus the square root of 100 plus 12. So that's going to be 112 all over 2. I'm going to factor this 112. What's that going to be? Let's get our calculator out here and look at this. Oh, this is a different looking calculator. I don't know what happened here. Okay, 112 divided by, I'm going to try 4 here. And that's divided by 4, so it must be divisible by 16. Let's try 112 divided by 16, which is 7. So this is going to be 16 times 7. So 16 is a perfect square. So negative 10, and if I take the square root of 16, it will be 4, and then 7 stays inside. Okay. 2 goes into 4 twice. 2 goes into negative 10, negative 5 times. So we end up with negative 5 plus or minus the square root of, or 2, the square root of 7. Okay. So overall, our solutions are negative 2, or excuse me, positive 2, because that's our, right, our solution there. And then we have negative 5 plus or minus 2 square root of 7. So in this case, we had one real solution and two irrational solutions, right? We have the square root irrational solution right here, okay? And so those are our solutions here, all right? Okay, so now what's going on here? We're going to do this. Oh, I was going to have, if that was extra space here. So looking here, this is what I want you to be careful with, okay? So this is a trinomial. We have that pattern of 4, 2, and then a number. So this is a quadratic form. And here's why it's going to be super important for you to make sure you factor using quadratic form whenever you can. So what's factors of negative 12 that add up to negative 4? That's going to be negative 6 and 2, right? So we can factor this. Factors of x to the 4th are going to be x squared and x squared. And then we have minus 6 and plus 2. Okay, and all that equals 0 because we're trying to find our zeros. So now we can set each of those factors, x squared minus 6 equal to 0, and x squared plus 2 equal to 0. Okay, so both of those factors equal 0. We're going to solve both of those. So I'm going to add 6 to both sides here. So x squared equals 6. And I can take the square root of both sides. That's going to leave me with x equals, don't forget your positive and negative, square root of 6. So there I have two irrational solutions. Then I'm going to subtract 2 up here. X squared equals negative 2. I'm going to take the square root of that guy. And you can see what happens here, plus or minus I squared root of 2, right? All of my solutions are either irrational or imaginary. Plus or minus square root of 6, and plus or minus I square root of 2. So notice I don't have any real solutions, right? Any irrational solutions. So if I would have tried to take all of my factors of 12 and divide it, I would have not have found any zeros. That's why it's important for you to make sure that you try to factor those first, okay? Otherwise, you're going to do lots of dividing. That would have been like what? 1, 2, 3, 4, 6, 12. So that's 6 factors times 2 is 24. You would have divided 24 times and not found a factor. That'd been a lot of work for no reason. So make sure you can recognize that quadratic form, okay? Next thing you want to make sure you can recognize is the factor by grouping. So make sure you can see that. So right here, I can see that I have this 4 and 2 is suspicious. So I'm going to see if I can factor this by grouping. I'm going to put this plus and negative right here so I can keep that negative sign in my group. 0 equals, and I'm going to factor out an x squared. That will leave me with a 2x minus 1. Factor out a negative 2 here. Oops. That will leave me with an, what's that? Positive 2x minus 1. And so we can indeed factor this by grouping. So we can pull the 2x minus 1 out. 2x minus 1 times my leftover x squared minus 2 equals 0. Once I get these factors, I can set them both equal to 0. So I have 2x minus 1 equals my 0, and x squared minus 2 equals 0. Okay, so plus 1 divided by 2, x equals 1/2. Okay, so we have that one. We do have one rational solution, so that's kind of cool. So I add 2 here. X squared equals 2 square root. X equals positive and negative square root of 2. So I have 2 irrational solutions and 1 rational solution. So I have x equals 1/2 and positive and negative square root of 2. Okay, so it's very important that you recognize again that factor by grouping and recognize your quadratic form. Okay, so next step is we're going to learn how to write equations. So it's really important you understand this conjugates theorem. So complex conjugates just says if I have a root 2, 5, and 3i, well, 2 and 5 are rational, so they just stand alone. They don't need buddies. They don't need twins. They're fine. But 3i, that has to have a conjugate. Okay, so if I have a root of 3i, that means I have to also have a root of negative 3i. It has to have a conjugate. Okay. Same thing with irrational conjugates. Anytime I have a square root, it has to also have a conjugate. Okay. So if I have root 6 and negative 2 square root of 3, the 6 is standalone because it's just a rational root. But this one right here, if I have a negative 2 square root of 3, I must also have a 2 square root of 3. Okay. And so make sure you understand those conjugates. They are always, always twins, right? They go hand in hand everywhere. They do not go anywhere without each other. Okay. So right here, we're going to write a quadratic function, p, in standard form. So we have to multiply it all out with rational coefficients that has the root 2 plus 5i. Well, if it has the root 2 plus 5i, we must also have the root 2 minus 5i as well. Okay. When we write our factors, so if this is a root, we can actually put it in factored form. It's always going to be x minus my 0. Okay. So that's how you write it in factored form. And so in this case, we're going to put in our p of x, which is going to be our function here, equals, and we're going to write it in factored form. X minus my 0, in this case, 2 plus 5i. Okay. And we're going to multiply that by our other factor, x minus my other 0, right here, 2 minus 5i. Okay. And the first thing I'm going to do is distribute this negative to both of these binomials here. Okay, so that will end up being x minus 2 minus 5i, then x minus 2 plus 5i. Okay. Now to multiply these guys, this is just straight up multiplication, practice, and order of operations and all that good. It's not even order of operations, it's just straight up multiplication. Okay. So first thing I'm going to do is take my x here, and I'm going to go x times x is x squared. And then x times negative 2 is negative 2x. And then x times 5i is going to be plus 5xi. Okay? Then I'm going to get a different color here, and I'm going to take my middle term here. Negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times 5i is negative 2. Oh, sorry, not negative 2. Negative 10i. Okay. Then I'm going to get a different color. Let's go green this time. And I'm going to do my last one. Negative 5i times x is negative 5xi. Negative 5 times negative 2 is positive 10i. And negative 5 times positive 5i is going to be negative 25i squared. Okay. Remember this right here. I squared is always equal to negative 1. Okay. So we're going to fix that. Okay. So now we're going to simplify all these terms. So my x squared goes here. Okay. Then I have my x term 2x and negative 2x, and negative 2x is negative 4x. Right. Then I have my xi term. So 5xi, negative 5xi. Well, that's nice. They go away, right? They cancel. Then I have my 4. That's it. So I go plus 4. Then I have my negative 10i, my positive 10i. Those go away. And all I have left here is my minus 25. And for I squared, I'm going to plug in negative 1. And now it's pretty nice and neat. I'm just going to go equals x squared minus 4x plus 4 plus 25, which is now going to be x squared minus 4x plus 29. And that is my function p of x. So if I were to solve this with my quadratic formula, I would end up with those zeros, 2 plus 5i and 2 minus 5i. 2 plus or minus 5i. Okay? And that's how you write an equation from polynomial, given certain roots. Right? Let's go one more here. So now we have 3 and 4i. And so if I have 4i, I must also have a root negative 4i. Right? Okay? That's how I'm going to get a third degree polynomial. I should have 3 zeros. It's going to be q of x this time. I'm going to go x minus 3 times x minus my 4i times x minus my negative 4i. Okay, I'm going to simplify that. Whoops. My black here. X minus 3 times x minus 4i times x plus 4i. Okay. And one thing I'm going to tell you here is whenever you have these imaginary factors here, always multiply these together first, because your imaginary numbers or radicals will cancel each other out. If they don't cancel each other out, then you did something weird. Okay. So I would always make sure you multiply these guys together first. So that will be x squared plus 4xi minus 4xi. So you see that going away. Minus 16i squared. Okay. And so you can kind of see these guys here. Whoops. Black. Right here. These two right here cancel each other out. Boom. Okay. So we end up with our x squared minus 16 times negative 1, which is x squared minus or plus 16, right? And then, of course, I still have my x minus 3. Okay? And multiply those guys out. X times x squared is going to be x cubed. X times 16 is plus 16x. Negative 3 times x squared is negative 3x squared. And negative 3 times 16 is negative 48. So my q of x equals x cubed minus 3x squared, this is standard form, plus 16x minus 48. And if I were to solve for that guy, I would end up with those zeros of 3 and plus or minus 4i. Okay? All right, so that was for extra space. So in summary, here's some pretty important kind of properties for roots. So a real number r is a root of a polynomial p of x equals 0. Okay, so if r is my root, and if I plug p of r into the polynomial, it should equal 0. Okay, that's this part right here. R is also an x-intercept of the graph, so if it's a root, it should be on the x-axis, where it crosses the x-axis. X minus r is a factor of the polynomial, and when you divide the rule for p of x by the factor x minus r, the remainder should always be 0, and then x is a 0 of the polynomial. So those are all just properties we've talked about. These are kind of a little bit more summary, that when I divide by a 0, I should get a remainder of 0, and then x minus 1 is a factor. This is how I write our zeros: x minus my root, x minus my root, x minus my root, and those are all factors. And those roots are where it crosses the x-axis, which are also called zeros. Okay? So you have an Excel in Google Classroom. Do not forget to submit your correct work, not just a bunch of chicken scratch that's not correct. Number all of your problems, put the work for all of your problems, and make sure you have the correct work for all of your problems. Okay? And then I'll see you guys at your next Zoom. All right? Have a good day. Bye-bye.